The chosen research area is the study of the effects of dielectric spectroscopy in liquid mixtures with changing complexities. Dielectric spectroscopy is a measure of a material's dielectric properties as a function of frequency determined by the interaction of an external electromagnetic field and the electric dipole moment. The dielectric properties of all materials are dependent on its molecular structure, causing these properties to vary across materials.
The permittivity is the complex friction-dependent property of a material, used to indicate how materials interact with EM fields. Because it is friction-dependent for a time-varying electric field, it is defined by the equation seen, with its real and imaginary parts. For lossy mediums, such as dielectrics, the energy within a propagating EM wave is lost due to absorption per unit distance. This loss is quantified by the dielectric loss factor L, where tan delta is the loss tangent defined by the imaginary over the real part or the dielectric conductivity sigma on the angular frequency times the permittivity of free space. Typically, for good conductors, the conductivity is larger than the product of omega and the permittivity of free space. From this, the relative complex friction-dependent permittivity of a lossy medium can be more accurately defined as seen, with the imaginary part being the loss tangent, which causes attenuation of the propagating EM wave.
Recently, there has been much research in the applications for use of dielectric spectroscopy to detect internal properties of different enclosed bodies. This has been especially so in the areas of medicine and agriculture, where it is not always convenient to penetrate a body to determine properties of its internals. For example, in the medical area, electrical bioimpedance spectroscopy, EBIS, is viewed as a non-invasive measurement method to determine total body composition, segmental body composition, and respiration rate. Considerable advancement has been made in EBIS due to the development of more accurate systems in areas such as glucose concentration measurements.
In this analysis, the liquid mixture model was assumed to be homogeneous, isotropic, and linear. This was due to the infinite combinations of elements with varying properties that can be contained within a mixture. The permittivity of a material, in addition to frequency, is also a function of temperature. However, the effects of this parameter is fixed according to the particular problem being investigated. This image shows the reduction of the 3D model to a 2D version, generated by looking at a cross-section of the 3D model taken through the sensors.
As can be seen by the animated slide, as the frequency increases for a particular permittivity, the electric field decreases in strength. Additionally, there is more equipotential across the entire surface, or the entire surface of the dielectric mixture. Additionally, as the value of epsilon increases, the rate at which this happens also increases. As can be seen from the graph, the impedance magnitude increases with the decrease in permittivity, and it decreases exponentially with an increase in frequency. Additionally, the impedance phase increases as permittivity increases and also increases exponentially with an increase in frequency. The resistance increases with an increase in permittivity and also increases, but exponentially, with an increase in frequency. This is also the same for the reactance, as the reactance increases both with permittivity and increases exponentially with frequency. The capacitance increases with an increase in permittivity, and it also increases by exponentially with frequency up until 300 kHz for a value of permittivity of 200. It then remains constant. The value at which permittivity remains constant at for each permittivity increases with frequency. The loss tangent decreases exponentially with an increase in frequency and increases with a decrease in permittivity. The loss factor decreases exponentially as frequency increases and is constant with changes in permittivity. The average resistance increases exponentially as permittivity increases, and the average capacitance decreases almost linearly as permittivity increases.
Future applications. In the area of medicine, patients using ventricular assistance devices are at high risk of thrombosis due to blood coagulating faster when it comes into contact with artificial surfaces. This technique can be used to determine the resistivity of blood in real time to allow for optimal administration of anticoagulation medication. Dielectric spectroscopy has also been used to detect changes in body tissue for purposes of detecting cancer.